So when we left off last time, we were talking about measures of center and spread. We did the mean, median, and mode, and then we talked about range and standard deviation. We briefly mentioned quartiles, percentiles, and stuff like that. Talked about what the meaning of a percentile is. We're not going to go over how to calculate percentiles because at this point it's not overly important to us. But there is one application of the center and spread that I do want to go over. Actually, two very closely related applications, I should say. The first one, we found the mean and we found the standard deviation. And we said the standard deviation was definitely the best measure of spread that we had. For the mean, we said the mean or the median, depending on the set of data. In many cases, the median was actually a better measure of center than the mean was. If we had those extreme values, really large or really small values, the mean could change a lot where the median was pretty stable. But if we have a good set of data, a relatively normally distributed set of data, the mean and the median should be either the same number or really close to the same number. So that mean and standard deviation describing the center and the spread, and we're talking basically about a bell curve like this. Now, we said mean, median, mode are measures of center. That's talking about the center of the curve here. So this would be the mean, or the median or mode, but we're using the mean for right now. The standard deviation then describes the spread, and here's how it works. If I go one standard deviation below the mean right here, I'm going to label that -1 SD for -1 standard deviation. 34% of all, if this really is a normally distributed set of data, 34% of all the values will be in that range. If I go another standard deviation down, -2 standard deviations, an additional 13.5% of the data will be in that range. And if I keep going to -3 standard deviations, there will be 2.35% in that range. And then outside of 3 standard deviations, below 3 standard deviations below the mean, it'll be 0.15%. Going the other direction, it mirrors that exactly. So 1 standard deviation above the mean plus 1 SD. There's 34% in that range. Plus 2 SD. There's 13.5% in that range. And plus 3 SD. There's 2.35%. And above that, 0.15%. Now I realize I just put a lot of numbers and a lot of symbols up there. Well, not necessarily symbols, but letters and stuff. What does it all really mean? Well, let's say that for this course, good morning, Cody.
Morning.
Let's say the mean score for students in this course is an 84 out of a possible 100. With a standard deviation of 6. So going down here, the mean is 84. I put 84 there. The standard deviation is 6. When I move to the left, I'm going to subtract the standard deviation. I'm going to subtract 6. What's 84 minus 6? 78. Minus another 6. 72, and minus another 6. 66, right? Going up, adding a standard deviation to 84. 84 plus 6 would be 90. Another 6. 96, and one more. 102. What this all means now is, let's say you wanted to know what percent of students score above 90%, or above 90. Well, if I look over here, here's the 90 right there. Above 90, that would be this range right here. If I add those percents all together, it would add up to 16. So that would tell me that 16% of all students score above 90 for the course out of 100. Does that make sense? Or if I want to know what percent of the students score below an 84. Here's 84. So below 84 would be this way. If I added all those up, what would I get? Well, it's exactly half of the curve, so that should add up to 50%. 50%, half of all students, 50% will score below an 84. Let's say I want to know what percent will score between 78 and 96. Well, here's 78, here's 96. If I add those together, I'm going to get 81.5%. Now you might be looking at this saying, okay, that's kind of neat, but a little confusing. The big thing here is the numbers down here, these numbers came from the mean and the standard deviation. Those numbers change depending on what the mean and the standard deviation of your data set are. These percents up here always stay the same. Those will never change. So if I'm looking at a set of numbers that should be approximately normally distributed, most sets of natural numbers are approximately normally distributed, I can start out by drawing my bell curve. Pretend that looks somewhat symmetrical. What's that? Well, it all depends. I'm not a big fan of a bell curve as a grading system, no. I think that you should be measured against the standard, not against your other students. And that's what a bell curve does, is it measures you against other students. I'll show you a little bit here in a little while about how bell curve, well, how that whole idea works. If rather than comparing you to a standard, you compare you to everybody else in the group. I'll show you a little bit about how that works. So the percents are going to stay the same. 34% here, 13.5%, 2.35%, 0.15%, what's going to change is the numbers along the bottom. Now, right now, we haven't said anything about what we're looking at yet. Let's say you're considering buying a new home, and you decide you want to get a 3-bedroom, 2-bath home. And in the area that you were looking, you do some research, and you find that in that area, the mean sales price for all 3-bedroom, 2-bath homes is $134,000.
Now, how would you get to $140,000 looking at other prices at other homes?
You'd have to look at all homes. You may have to pick a time frame of 2 years or whatever. Look at all homes that were 3-bedroom, 2-bath that had sold in that area. Pick your area that you're going to look at. Find them, and then you'd have to find them. You'd have to add them up and divide, and then you have to do the standard deviation. If you're doing more than 5 or 6 numbers for standard deviation, you're going to use some sort of electronic device most likely to help you. Because you've seen that 6-step process. I would not sit there with 20 numbers or 30 numbers and crank out a standard deviation. And I would never ask you guys to do that, just so you know. So anyway, let's say we have a standard deviation of 32,000. So what that means down here, and I'm going to leave the zeros off just to shorten it up. The center of this curve is the 134,000. What's this number going to be then? What am I going to do to the 134,000? I'm going to subtract the standard deviation of 32. So 134 minus 32 is 102, like that. What comes next? 102,000 minus another 30,000 would be 70,000. Minus another standard deviation minus another 30,000 is 38,000. Going the other way, adding a standard deviation, what's going to go here? $166. Another 32,000, it's going to be 198. This will be 230. Correct? Everybody see what? Anybody have any questions where those numbers came from down there? Okay. So now that we've done that, we've filled out this little bell curve. Let's say that you find a house that you absolutely love. It's beautiful, it has everything you want, and you think this might be the house. And you put in your offer or whatever, and you get back what the lowest price the homeowner would take, and it comes up to be $198,000. Is that a good deal? Well, yeah, it may have a lot of things and stuff that you like, but $198,000 hits the curve right here. If I add up all these numbers, and the reason I would add up those numbers is because what I'm going to ask is what percent of the houses that are the size I want would be cheaper than this. Well, if we add up those numbers there, we find that 97.5% of all 3-bedroom, 2-bathroom houses in this area that have sold for less than $198,000. So what that's telling me is there's a good chance I can find a house that fits my needs that is cheaper than $198,000. Does that make sense? Okay. We could go a step further with this into something called normal probability.
So you add up
All these percents, yeah. Or what you could do, if it's easier, and that's what I normally do, because you know that this whole curve adds up to 100%, I would just add up these two over here and subtract them from 100, because it's quicker. Because that adds up to 2.5, so 100 minus 2.5 is 97.5. Because you know the whole thing has to add up to 100%. We're not getting into probability in here. That would be one of the next steps if we were going in a full-blown statistics class. And that's where the normal probability would come in. In a full-blown statistics class, we would move on and we'd actually start calculating normal probabilities. What we're doing up here has a name. It's called the empirical rule. What's that? You know, I'm not sure if the Romans came up with it or not. That's a good point. The being named empirical, it sounds like something that would be Roman, yes. All it is just an approximation and these numbers actually, it's not really exactly 34%, it's like 34.3% or something like that is what it comes out to be, or 1.3. These are just approximate. But what it does allow you to do is if you have a mean and standard deviation, you can make some really quick estimates. Because you can memorize these numbers. I have these numbers memorized. Of course, I use percents and probabilities maybe a little bit more than many of you will. But it's not that hard to memorize those numbers and use them, where you can say, okay, even if we're not exactly 166, we're close to 166, so we can use these percents to make an approximate judgment on things. If we needed to be exact, that's where the actual normal probabilities would come in, is you could take an exact value in between. Let's say it was 171. Well, we could actually find the exact percent or probabilities from the 171, or less than or greater than for the 171.
Isn't that a big sheet for a 2-bedroom or 3-bedroom, 2-bath, you said?
Yeah? What'd you say, a bit cheap? Mm-hmm. I don't know. I'm just throwing numbers out there. I don't know how realistic they are. But actually, around this area, $134,000 about 2 years ago was not a bad price. That's pretty cool, but you'll remember home values crashed. If you look back to like 2007, 2008, Yeah, a 3-bedroom, 2-bathroom house, even around here, probably pushing 155, 160. But those were never really worth that value. It was just kind of a bubble, a market bubble that everybody was paying more than they should have at that time.
Home is kind of at a nice little upright since that crash.
Yeah, I mean, well, that's why a lot of people ended up turning their homes over to the bank was the bubble. It made it look like houses were worth more than they were because everybody was paying these huge prices for houses. Well, then when the market kind of crashed, the bubble burst, people were in these houses they had just bought, and the house wasn't worth what they owed on it. Now, technically, you don't take a loss on it till you sell it anyway, so you could have just sat with them and made the payments and hopefully waited out. But many people had ended up walking away because the house wasn't worth near as much as what their loan on the house was.
You refinance at that point?
You could, well, no, actually, you can't refinance because the house isn't worth enough to cover the collateral for the loan. I won't get into the big finance part of it, but there are issues with private mortgage insurance, PMI. Normally, you have PMI on your mortgage for the first 5 or 10 years until you get it paid down to a certain percentage of the value of the house. Well, when the market crashed and now you owe, $150,000 on a house that's only worth $120 now. Well, before you can get rid of your private mortgage insurance, you got to pay that $30,000 down, and then you got to pay down below the value of $120. Yeah, so I mean, it was expensive for homeowners because there were extra expenses associated with your loan being greater than the value.
And then if you want to break even on that, you may have to tell me energy costs.
Yeah. Okay, so there's another tool related to that mean and standard deviation that allows us to do some comparisons with our numbers. It's called a z-score. What a z-score does is it kind of tells us where on this curve a number would fall. What point would it be between the mean and what standard deviation or whatever is that value going to be? And it doesn't give us probabilities or percents or anything, but it does allow us to compare two numbers from different populations that normally we wouldn't be able to compare. For example, to start school here, pretty much all of you had to take some sort of a placement test or an entrance test. And I'm going to oversimplify it here a bit. We're going to say that there is an English and math portions to that test. And let's say that on the English portion you scored 28, and on the math portion you scored 24. Now you might be tempted to look at that and say, hey, I did better in English. I scored a 28. But that might not be true. Maybe the math portion is harder. Or how do you know? I mean, they weren't the same test. If you took the English test twice and scored a 28 and a 24, well, then you could say I did better on this one because I took the same test and I had a higher score. But when we have two things like this that are completely different, how do we compare them? Well, we compare it to things within its own population, within its own group. We talked a little bit about that idea of a population being all of the items that we're interested in. When you take a placement test, it's not just your score that you're interested in. It's the score of everybody else who's ever taken that placement test. And where you sit in that group is what matters. A z-score is found by taking the value, which we're just going to label x, subtracting the mean, and then dividing by the standard deviation. So let's say that on the English test, the mean is 25. And the standard deviation is 2. Let's see over here on the math test. I don't know why I wrote math. The mean is 22. The standard deviation is 1. Now looking at this even, you might be tempted to say, hey, I scored a 28, the mean was 25. I was 3 points above the mean. Over here, I scored a 24, and the mean was 22. I was only 2 points above the mean. So the English is still looking like a better score, isn't it? But we have to take into account that spread of the curve, the variance, or the standard deviation. So let's calculate the z-score. So this z-score is going to be 28 minus 25 over 2. (28 minus 25 is 3 over 2. 1.5. So 3 divided by 2 is 1.5. What is that telling us? What a z-score tells us is how many standard deviations away from the mean we are. This is a positive 1.5, so it's telling us that that score is 1.5 or 1.5 standard deviations above the mean because it's positive. If it were negative, it would be below the mean. I'll show you an example of that in a second.
You want to be below or above the mean.
Depends on the situation. If you're looking at what your test score is, it'd be nice to be above the mean. If you want to look at job performance, it'd be nice to be above the mean. If you want to look at your debt, it would be really nice to be below the mean. So it all depends on what you're looking at. Whether it's if you're looking at a good thing, it's nice to, something that's having a large number is good, you want to be above the mean. If it's something where having a smaller number is good, then you want to be below the mean. Like time it takes you to do a job. Well, that'd be nice to have a smaller number. It'd be nice to be below the mean for that. So it'd be nice to have a negative z-score. So my z-score for the math over here, we got 24 minus 22 over 1. 24 minus 22 is 2. Divided by 1 is 2. What's that z-score 2 mean? Well, that score on the math is 2 standard deviations above the mean. So which one's better?
Math.
Math. In math, you were 2 standard deviations above the mean. You could go back to that curve up here. 2 standard deviations would be right here. There's only like 2.5% that scored better than you in math. The English is somewhere in here at 1.5 standard deviations. Well, we don't know how to divide up the percents there, but we know it is lower. There's a higher percentage of people that scored better than you in the English than there was in the math.
So
Your math test was more impressive. Let's look at another example of that. Let's say you are managing a large department store, retail type store like a Walmart or Shopko or whatever that has several different departments. And you have been told that you're going to have to get rid of 1 salesperson. And you have it narrowed down to 2. 1 salesperson works in toys, and the other one in electronics. And you have decided whoever has the worst week next week is the one you're going to fire. But you have to be careful. Depending on the time of the year, like if it's around Christmas, I suppose the toys might be kind of popular. But most of the time, there's more electronics that sell on average than toys. Also, electronics tend to be more expensive than toys. So 1 or 2 electronic items might be a huge deal. We don't have to give them names, just the toy person or the electronic salesperson. Let's say that we keep track of their sales for the next week, and the person in toys has sales of $1,800 for the week. Not terrible, no. Person in electronics has sales of $2,700. Yeah, they may have sold a $700 television that was, a fourth of their sales. Yeah, very, very good point. So now, go ahead.
Well, I was going to say, then again, some Lego set toys would be.
Yeah, there's some toys that can be pretty pricey too. Yeah. So now what we're going to do, we can't necessarily compare them to each other because we're not comparing apples to apples. So the way we do it is we compare them to their whole population. how does this person in toys rank against everybody else in toys? And to do that, we're going to use a Z-score. We find the mean sales for everybody in toys for that week came out to be $2,400 with a standard deviation of $200. In electronics, the mean sales of every salesperson in electronics that week came out to be $3,500 with a standard deviation of 300. So now I want to find out which one did worse. We're going to use a Z-score. So this one, 1,800 is their sales minus the mean of 2,400 divided by a standard deviation of 200. So that's a negative 600 divided by 200 is a negative 3. What's that negative 3 stand for? It's very bad. It's negative, so you're below the mean, and your sales are a good thing, so you'd rather have a high score, right? It's negative, so you're below the mean. Negative 3 means you are 3 standard deviations below the mean. Over here, Z-score is going to be the sales of 2,700 minus the mean of 3,500, which is a bigger gap, isn't it? That's 800 below instead of 600 below. Yeah, we subtract again negative 800. Divided by 300, though, is only a negative 2.67. So that person was only 2 2/3 or 2.67 standard deviations below the mean. Still not a good performance, but not as bad as the person in toys. But you can see what we did is we compared them back to their own population, here finding the Z-score, and then we were able to use that to compare them to each other. Make sense? Yeah. Buy electronics, huh? Okay, well, I'm going to end that. That is all of our new material. That's the last of what we need to cover.